Hello everyone, we are West Coast Innovators. My name is Gabriel Pina. I'm the CAD leader, the structural engineer. Our project manager and geotechnical engineer is Max Gray. Our water resource engineer and our structural engineer is Marco Estrada. Our site civil engineer is Jay Rowerdink. Our environmental engineer is Carlos Villarino. Our team decided to work on the Coronado Pedestrian Tunnel project. Coronado Island has only two roads on which people can enter and leave the island, one of them being the Coronado Bridge and the other being the Silver Strand Boulevard, which has enhanced the overcrowding effect many people are feeling as San Diego becomes a more popular destination for tourists and people looking to buy property. At these entrances to and from the island, motor vehicle traffic is very heavy, and bicycle and pedestrian safety is very minimal in regards to bike paths, intersection crossings, and speed limit. The Coronado Bridge entrance and exit, in particular, does not even allow people to cross legally on bicycles or walking, even after the first intersection reaches the island. This is critical because State Route 75 is actually intersecting a known and functioning bike route on the island. The previous solution to this problem was to take the Strand bike path either along the golf course on the south side of the bridge or park on the north side of the bridge, about a half mile down and cut under the bridge right before the bridge begins to go over the bay. While this solution has up to the point been adequate, a new approach to the problem has been thought up, designed, and seems to be an improvement.
Methods considered for this project included using a bridge over SR-75, cut and cover, or the use of a tunnel boring machine. A bridge was quickly ruled out as residents in the area did not want their view obstructed, and a cut and cover was also quickly ruled out due to the fact that SR-75 is the most prominent entrance into Coronado and could not be blocked. Because of this, our team decided to use a tunnel boring machine for the construction of this project. The scope for this project included the following: site civil, geotechnical, structural, and hydrology and storm drainage. To begin this geotechnical investigation, I was given a CPT or cone penetration testing data provided to me by Professor Valdez. Using this data, I was able to analyze and classify the soil for our site. The soil encompassing the site was determined to be mainly sandy silt and silty sand. We were also able to determine the location of the water table for our site, which was right at ground level. Using the USGS site, the team was able to analyze the past decade of seismic activity in a range of 50 miles in any direction from the project location. From the start of 2008, there had been 21 seismic events within the said range, and the average magnitude of these events was calculated to be 2.9, with the greatest being 4.5. The average depth of these events was 6.7 miles below the surface, with the largest and smallest depth being 10.6 and 0.6 miles. The amount of earthquakes and average magnitude calculated shows that the site is infrequently affected by earthquakes, and when an earthquake does occur, it will not be big enough to have any effect on the structure. The earthquakes recorded in this time frame are estimated to have produced a peak ground acceleration of 0.01 g at the site. Accelerations of this magnitude are not expected to produce damage. For analysis purposes, we assumed a 365 meters per second shear wave velocity. Using this in the location of the site, 0.41 g earthquake has a 10% probability of being exceeded in a period of 50 years, whereas the maximum considered earthquake has a 2% probability of being exceeded in a 50-year period. The maximum considered earthquake would produce a ground acceleration rate of 0.65 g. The recommendations that can be made after the geotechnical investigation are that the tunnel can and should be supported with reinforced concrete because the soil will not generate enough pressure even when saturated to affect the structure. With the water table being so high, it is recommended to dewater the location before construction begins. However, post-construction, one fear the team had was that the hydrostatic uplift created by the water table underneath the structure would cause it to float. This was, however, determined to not be a problem as the tunnel was long enough and heavy enough to avoid this force.
There were many other factors that influenced our tunnel design, one of which being the length of the roadway that we must cross. Our final decision was to make the tunnel 187 feet long. According to the Department of Transportation Highway Design Manual, the walkway must be at least 12 feet wide, so we had to make sure that we met that requirement. We also had to meet the requirement of 12-foot clearance for all pedestrians and bicyclists. So we had an inner diameter of 18 feet and then an outer diameter of 21 feet. In order for our tunnel to be accessible to all users, we had to keep a consistent slope of 2% or less throughout the entire pathway and tunnel.
Due to this structural design of the tunnel, a new grading plan had to be created with 382,000 cubic feet of soil, either finely graded or excavated, to allow for pedestrians and bicyclists to safely ascend and descend the new 25-foot elevation change from the foot of the tunnel to the existing grade. Because of this large amount of grading, another concern that had to be addressed was the ADA and Department of Transportation bicycle design manual requirements for maximum allowable slope on bicycle and pedestrian paths. Because of this requirement, each segment had to be specifically designed with particular curvature in order to allow more horizontal pathway over which to rise and fall in elevation. The 10 segments were divided up, and elevation changes and cross slopes were designed to allow for optimal safety for users with regards to the proposed pathway vertical and cross slopes.
With the new pathways downsloping into the tunnel, the flow of water into the tunnel must be considered. The proposed project leads to the creation of the north and south basins, so named with respect to their location of the tunnel. Having areas less than an acre and with the aid of the San Diego County Hydrology Manual, a peak flow rate was determined for runoff into each entrance. Storm grates placed at each entrance will allow water to flow into the troughs that lead to storm drain pipes to send the runoff to the main storm drain. Due to the low HGL at the trough exit and higher HGL of the storm drain entrance, pumps that provide 20 feet of head have been deemed necessary for proper operation. Now to the structural components of the project. On the west side of each pathway, a retaining wall will be placed. This will prevent soil from sliding in on the pathway, ensuring safety for all pedestrians. The wall will be 16 feet tall with a differential elevation of 12 feet. The detailing of the retaining wall using a 12-inch concrete masonry block have been included in a plan view on this slide and is to MSJC code.
The recommendations that the team has made based off analysis and recommendations from both the site civil and geotechnical teams is that the tunnel should be bored and designed with reinforced concrete using 32 number 9 bars. The geotechnical team confirmed the soil type and properties to be a sandy silt that would be saturated upon the project's completion. The amount of pressure exerted on the tunnel by a saturated soil at ground level was calculated to require a large area of steel bars. To meet this requirement, the team elected to use the chosen ones.
Stormwater Pollution Prevention Plan, or also known as the SWPPP, for the Coronado Gateway Pedestrian Tunnel, will reduce the short and long-term impacts on the receiving water quality. The receiving waters come from the Alvarado and Otay areas, which are about 20 miles from the construction site. Some of the inland surface water beneficial uses for the Coronado Tunnel were identified as municipal and domestic supply, agriculture supply, industrial service supply, contact water recreation, and non-contact water recreation. Some of the pollutants of concern for this project are heavy metals, phosphorus, and sediments. The Coronado Pedestrian Tunnel will also include low-impact development practices that include features that attempt to mimic natural hydrologic conditions for water quality design. And lastly, the best management practices consist on a bioretention system.
The detailed summary for the cost estimate that was done on the project is shown here. As can be seen on the left, each small task was designated into a category with a task code, and the cost for these larger categories of tasks was calculated to see where the most money will be spent. The total cost for the entire project came out to be $8.6 million. The largest portions of this cost came from the site preparation section and the tunnel boring machine rental and operation section. The site preparation cost is relatively high because of the large amount of fine grading and excavation needed for this particular project, and the tunnel boring machine chosen for the construction of this tunnel is top of the line and ensures the best possible quality when excavating and placing shotcrete. All things said and done, this report effectively investigated the existing conditions of the proposed site, designed a structurally sound solution to the given problem, and provided all working materials at a reasonable price. This project was also designed to allow for a reasonable construction schedule and phasing process, so as to make the construction environment as unobtrusive as possible to the local residents and visitors to the island.